There are questions in physics so fundamentally disturbing, so deeply paradoxical, that they have kept the greatest minds in science awake for decades, staring at the ceiling, wrestling with contradictions that seem to tear at the very fabric of reality itself. Stephen Hawking spent his entire career confronting these paradoxes, and what he discovered was far more unsettling than anyone imagined. These aren't just academic puzzles to be solved, but fundamental cracks in our understanding of the universe that suggest reality itself might be far stranger and more fragile than we ever dared to believe. These paradoxes don't just challenge our theories, they challenge our sanity. They force us to confront the possibility that the universe operates according to principles so alien to human intuition that even our most brilliant scientists can barely comprehend them. And according to Hawking's analysis, some of these paradoxes might not have solutions at all, but rather reveal that the universe itself is fundamentally paradoxical. What if I told you that Stephen Hawking identified paradoxes in physics that suggest time might not exist, that information can be in two places at once, and that the act of observing reality might actually create it? That these aren't philosophical curiosities, but mathematical certainties that have driven some of the world's most brilliant physicists to the edge of madness. This is the story of the paradoxes that haunted Stephen Hawking's dreams and continue to torment physicists today. Contradictions so profound that they might reveal the universe to be far more mysterious and terrifying than we ever imagined. Before we explore the mind-bending paradoxes that kept Stephen Hawking awake at night and continue to challenge our understanding of reality itself, hit that subscribe button because we're about to dive into the deepest mysteries that physics has ever encountered. Stephen Hawking's fascination with paradoxes began early in his career when he realized that the most profound insights in physics often emerge from apparent contradictions that force us to abandon our preconceptions about reality. The physicist understood that paradoxes aren't obstacles to understanding. They're doorways to deeper truths that our limited human intuition struggles to grasp. The first paradox that tormented Hawking was what he called the information paradox, a contradiction so fundamental that it threatens to destroy our understanding of both quantum mechanics and general relativity simultaneously. This paradox emerges from the collision between two of the most successful theories in physics, and its implications are so disturbing that many physicists refuse to fully confront them. The information paradox begins with a simple question: what happens to information when it falls into a black hole? According to quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, or transformed, but never completely eliminated from the universe. This principle, known as unitarity, is one of the foundational pillars of quantum theory. But black holes seem to violate this principle catastrophically. When matter falls into a black hole, it appears to disappear completely from the observable universe. And when the black hole eventually evaporates through Hawking radiation, that radiation appears to be completely random and thermal, carrying no information about what fell in. Hawking's calculations suggested that information really is destroyed in black holes, which would mean that quantum mechanics is fundamentally wrong. But if quantum mechanics is wrong, then our entire understanding of atomic and molecular physics collapses. The paradox forces us to choose between abandoning quantum mechanics or accepting that the universe can delete information. Both options are equally terrifying. The physicist spent decades wrestling with this paradox, initially believing that information was indeed destroyed, then later changing his mind and proposing that information somehow escapes in the Hawking radiation. But his proposed solutions only created new paradoxes, each more disturbing than the last. Think about the implications of the information paradox. If information can be destroyed, then the universe is not deterministic. The future cannot be predicted from the present, and causality itself becomes meaningless. But if information cannot be destroyed, then black holes must somehow encode and preserve every detail of everything that ever falls into them, which seems equally impossible. The second paradox that haunted Hawking was the measurement problem in quantum mechanics, a contradiction so profound that it suggests the act of observation might literally create reality. This paradox emerges from the bizarre behavior of quantum systems, which exist in multiple states simultaneously until they are observed. According to quantum mechanics, particles don't have definite properties until they are measured. An electron doesn't have a definite position or momentum until someone observes it. Before measurement, it exists in a superposition of all possible states simultaneously. This isn't just a limitation of our knowledge, it's a fundamental feature of reality itself. But this creates a paradox. If particles only have definite properties when observed, what constitutes an observation? Does a human observer create reality by looking at it? Does a measuring device count as an observer? What about a computer, a bacterium? Where exactly does the quantum world end and the classical world begin? Hawking realized that this paradox has terrifying implications for our understanding of reality. If consciousness is required to collapse quantum superpositions, then reality might not exist independently of observers. The universe might be fundamentally dependent on conscious beings to give it definite properties. Without observers, reality might remain in an eternal state of quantum limbo. The physicist explored various solutions to the measurement problem, from the many worlds interpretation that suggests every quantum measurement creates parallel universes, to theories that consciousness itself is a fundamental feature of physics. But each solution created new paradoxes that seemed even more disturbing than the original problem. The third paradox that tormented Hawking was the grandfather paradox, and its implications for the nature of time itself. This paradox emerges from the possibility of time travel, which is permitted by Einstein's general relativity under certain extreme conditions. The grandfather paradox asks, what happens if you travel back in time and prevent your own birth? If you succeed, then you were never born, so you couldn't have traveled back in time to prevent your birth, which means you were born after all, which means you could travel back in time to prevent your birth, and so on in an infinite loop of logical contradiction. Hawking initially hoped that physics would somehow prevent time travel paradoxes from occurring, proposing what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel to the past. But his own calculations revealed that this protection might not be absolute and that time travel paradoxes might be possible under certain extreme conditions. The implications of time travel paradoxes extend far beyond science fiction. If the past can be changed, then causality becomes meaningless and the entire structure of logical reasoning collapses. The universe would become fundamentally unpredictable and chaotic, with effects preceding their causes and logical contradictions becoming physical realities. Let me ask you something that might fundamentally change how you think about the nature of reality. If these paradoxes have no solutions, what does that tell us about the universe itself? Share your thoughts in the comments below, because this question strikes at the heart of whether reality is comprehensible at all. The fourth paradox that kept Hawking awake was the fine-tuning problem, the disturbing observation that the fundamental constants of physics seem to be precisely calibrated to allow the existence of complex structures like stars, planets, and life. Change any of these constants by even tiny amounts, and the universe becomes sterile and lifeless. This fine-tuning is so precise that it defies statistical explanation. The cosmological constant, which determines the rate of cosmic expansion, must be tuned to within 1 part in 10^20 to allow galaxy formation. The strength of the nuclear forces must be calibrated to within a few percent to allow the formation of complex elements. The mass of the electron must be precisely what it is to allow stable atoms. Hawking realized that this fine-tuning creates a paradox. Either the universe was deliberately designed by some intelligence to support life, or there are countless other universes with different constants, and we happen to live in one of the rare universes that can support observers. Both explanations are deeply unsettling. The design explanation suggests that the universe has a purpose and a creator, which conflicts with the materialist worldview that underlies modern science. The multiverse explanation suggests that reality is far vaster and stranger than we ever imagined, with infinite universes containing every possible combination of physical laws. But both explanations raise new paradoxes. If the universe was designed, who designed the designer? If there are infinite universes, why do we observe this particular one? The fine-tuning problem forces us to confront questions about the nature of existence itself that science may be fundamentally incapable of answering. The fifth paradox that tormented Hawking was the horizon problem in cosmology, the observation that distant regions of the universe that have never been in contact with each other have identical temperatures and properties. This uniformity seems to violate causality, suggesting that information traveled faster than light in the early universe. The cosmic microwave background radiation shows that the universe has the same temperature to within 1 part in 100,000 in all directions. But according to standard cosmology, many of these regions have never been in causal contact. Light hasn't had enough time since the Big Bang to travel between them. So how did they coordinate to have the same temperature? Hawking explored various solutions to the horizon problem, including cosmic inflation, the idea that the universe underwent a period of exponential expansion in its first moments. But inflation itself creates new paradoxes, requiring the existence of exotic forms of matter and energy that we've never observed, and raising questions about what caused inflation to begin and end. The physicist realized that the horizon problem might indicate that our understanding of space, time, and causality is fundamentally flawed. Perhaps information can travel faster than light under certain conditions, or perhaps the universe began in a state that already contained correlations that seem impossible according to our current understanding of physics. Recent developments in quantum mechanics have revealed even more disturbing paradoxes that would have fascinated and terrified Hawking. Quantum entanglement creates spooky action at a distance, where particles can instantaneously affect each other across arbitrary distances, seemingly violating the principle that nothing can travel faster than light. The physicist would have been particularly intrigued by the delayed choice quantum eraser experiments, which suggest that decisions made in the present can retroactively determine what happened in the past. These experiments seem to show that the act of measurement can reach backward in time to determine the properties of particles that were measured earlier. Even more disturbing is the quantum Zeno effect, which shows that the act of observation can freeze quantum systems in place, preventing them from evolving. This suggests that consciousness might have direct physical effects on reality, challenging the assumption that mind and matter are separate domains. Hawking also grappled with the paradoxes of quantum field theory, which predicts that the vacuum of space should have infinite energy density. This vacuum catastrophe represents the worst prediction in the history of physics. The calculated value differs from observations by a factor of 10^120, making it spectacularly wrong. The physicist understood that these vacuum paradoxes might indicate that our entire approach to understanding quantum fields is fundamentally misguided. Perhaps the vacuum isn't empty at all, but filled with structures and processes that we can't detect or comprehend with current technology. The paradoxes of quantum gravity presented Hawking with even more fundamental challenges. When quantum mechanics is combined with general relativity, the resulting equations become infinite and meaningless. This suggests that either quantum mechanics or general relativity, or both, must be wrong at the deepest level. String theory, which attempts to resolve these paradoxes, creates new ones by requiring the existence of extra dimensions that we can't observe and predicting the existence of countless possible universes with different physical laws. The theory that was supposed to provide a theory of everything instead suggests that everything we thought we knew about physics might be wrong. Hawking also confronted the paradoxes of consciousness and free will. If the brain is a physical system governed by the laws of physics, then all our thoughts and decisions are determined by prior causes. But if our choices are determined, then the concept of moral responsibility becomes meaningless, and the entire structure of human society is built on an illusion. Yet if consciousness can influence physical processes, as suggested by some interpretations of quantum mechanics, then the materialist worldview that underlies science is fundamentally incomplete. The physicist realized that consciousness might be the ultimate paradox, something that seems to exist but cannot be explained by the physical theories that describe everything else. The paradox of emergence troubled Hawking as well. How do complex properties like life, consciousness, and intelligence arise from simple physical interactions? The transition from non-living matter to living organisms, from unconscious processes to conscious experience, seems to involve the spontaneous appearance of entirely new categories of phenomena. This emergence paradox suggests that the universe contains creative principles that we don't understand, mechanisms that can generate genuine novelty and complexity from simple beginnings. But if such principles exist, they challenge the reductionist assumption that complex phenomena can always be explained in terms of simpler components. Hawking's final years were haunted by what he called the ultimate paradox, the question of why anything exists at all. Why is there something rather than nothing? This question seems to transcend physics entirely, yet it might be the most fundamental question we can ask about reality. The physicist realized that this paradox might be unanswerable in principle, Perhaps the existence of the universe is a brute fact that cannot be explained by anything more fundamental. Or perhaps the question itself is meaningless, based on assumptions about existence and causality that don't apply to reality as a whole. The paradoxes that kept Stephen Hawking awake at night continue to torment physicists today. They represent fundamental limitations in our understanding of reality, cracks in the foundation of physics that suggest the universe might be far stranger and more paradoxical than human minds can fully comprehend. These paradoxes force us to confront the possibility that reality itself is fundamentally paradoxical, that the universe operates according to principles that violate our basic assumptions about logic, causality, and existence. Perhaps the deepest truth about reality is that it cannot be understood by minds that evolved to navigate a much simpler and more predictable world. Hawking understood that these paradoxes might never be resolved, but he also recognized their value. They force us to question our assumptions, to push the boundaries of human understanding, and to confront the profound mystery of existence itself. The paradoxes that keep physicists awake at night might be the universe's way of reminding us that reality is far more wonderful and terrifying than we ever imagined. The next time you lie awake at night, remember that you're in good company. The greatest minds in physics have spent sleepless nights wrestling with questions that seem to have no answers, paradoxes that challenge the very foundations of rational thought. These mysteries remind us that despite all our scientific progress, we're still cosmic children trying to understand a universe that might be fundamentally beyond our comprehension. If this exploration of the paradoxes that haunted Stephen Hawking has kept you awake thinking about the fundamental mysteries of reality, make sure to smash that like button to support more deep dives into the questions that challenge our understanding of existence itself. Subscribe to our channel and hit that notification bell so you never miss our investigations into the paradoxes that continue to baffle the greatest minds in science. Share this video with anyone who's ever wondered whether reality makes sense at all, because these paradoxes might be the key to understanding the deepest truths about the universe. And let me know in the comments, which of these paradoxes troubles you the most? Do you think these contradictions will eventually be resolved? Or do they reveal fundamental limitations in human understanding? What other paradoxes in physics or philosophy keep you awake at night? Drop your thoughts below and join our community as we explore the questions that might never have answers but continue to drive the search for truth. The universe is full of mysteries that challenge everything we think we know, and sometimes the most profound insights come from embracing the paradoxes rather than trying to resolve them.